I had assigned a take-home exercise for today. Take-home exercise concerned a version of what I would term defect discovery. So it asked you to discover something that could be viewed as defects, the differences between two images, right? Image one, image two. No?
Yes.
Is this sounding familiar?
Yeah.
Yeah. And more than that, I asked for the that exercise to be followed in a structured way. So I asked you to record the timing of your discovery of different defects and how many you had found by different points of time, right? And you went through that exercise and found defects of various sorts involving flags and differences in the figures in different states, or a band, one versus a band and another, a marching band. But that wasn't really directly the point. The point concerned sort of the process of discovering these defects and features of that process, the dynamics of that process, how it played out over time. So can anyone say, reflecting on your experience, are there any things that struck you as sort of features of that process of discovering defects? Any characteristics of that struck you? Yes, Connor.
Like once I noticed a certain defect, I was had my eye out for it. So once I noticed like a character could be a different shape, or that more I realized there was like subtle differences, the more I was looking for like subtle differences. But then the more I was looking for subtle differences, the more I like missed big differences that I didn't see before.
Okay, that's interesting. So to a degree, you found a class of defects. Like you started to look for certain other examples of a class of defects, but that in some sense had an opportunity cost. It distracted you from finding other types of defects.
Yeah, like I was looking for bigger ones at first, like the obvious ones.
Yeah.
And then I started looking for like small ones.
Yeah.
And then I started noticing then I missed like the triangle tree difference one.
Yeah.
I was like, how did I not see this yet?
Yeah, totally. Yeah, been there, done that. Yeah. So I feel your pain. Yeah. So that's a good observation. Others. Yes, Rushak.
The way that like finding those defects work too, because I started outlining the entire United States map. And after I was done there, saw defects, I would then move like from top and then left to right, and left to right.
Oh, interesting.
Left to right.
Okay.
And I would do like those scans to find those.
Okay. That's interesting. So you evolved a sort of systematic method to visually search so that it was less hit or miss. Okay, so what I'm hearing in both of those is some element of learning, and focus in both cases. Like a focus visually at a point, or focus on a type of defect. You recognized there's some structure to it that you could take advantage of, and maybe it sometimes distracted you from other things that were left in your peripheral vision. Anyone else? Yes, Rob.
Yeah, the thing that I found was I found the first 10 errors within like 6 minutes or 7 minutes, and then it went like 10 minutes before I found another one, and then so everything happened like 90% of them happened right at the beginning. Like boom, 20 minutes I might find one, and that kind of diminishing resources after like 10 minutes.
Okay, so you found there's kind of a pulse initially, or burst, and then it sort of slowed.
Yeah.
Anyone want to elaborate on that at all? Did everyone find that?
Yeah.
Okay. Anyone want to elaborate on it at all? Like anything else you found? Yeah. So I think that's Ron in the back. Yeah, my eyes aren't quite.
So I also find what the bugs at the start, and then it would peter out. But then I'd also find that I'd have like lapses where I don't find bugs, and I found another bug. Yeah. And then I have like a pulse where I find a bug, and then back to
bingo. Yeah. So a lot of people find that they go through sort of a punctuated equilibrium with Stephen Jay Gould's description of it in A Wonderful Life. or wonderful life rather. So you sort of find them in bursts. You find a bunch, like Rob said. Sometimes then you don't find for a while, like he said, it slows, or you don't find any, and then maybe you find a different type. You're like, oh, the tree is of a different shape. Okay, now I'm on to, okay, I'm going to look for something. So that's an interesting point. And maybe it would have been different with Trushanks because he was scanning systematically. And it's an interesting question, like if a test team could do, two different types of scanning, you might find different types of process. You might find different types of defects. Anyone else want to comment on it? About the experience? Maybe I'll ask Ronan since Trushank has already commented. Yeah.
Yeah, for me, when I was doing it, I wasn't sure there were some things that were like I want to say copier errors, maybe.
Yeah.
Like some of the ink was a little
Totally. Like, is this spec?
Yeah.
Yeah.
I felt like I was reaching for some of that.
Yeah.
I wasn't too sure. So some people had like an extra 5 like defects found than me, and I was like, well.
Yeah. There's something like the wave shapes in the ocean.
Like
There were
Oklahoma had
there's yeah, Oklahoma had that's right. Yes. Yes, so Connor.
Yeah, like what Bro was saying, like at first I feel like I was thinking like, oh, that probably isn't one. I was almost looking if it was like one of those games, like to find the differences, and I was like, that probably isn't one. But I'm like, realistically though, we're looking for actual errors. So even if I was like, oh, this like dot's a bit different, I'm like, I'm gonna write it down because technically it is a difference, and we're looking for like small differences. It's still a difference.
Okay.
So.
Yeah. So you find sort of things on the margin. Yeah. Randall.
Yeah, I didn't notice. It's like since I didn't know the states, my description was kind of something.
Oh, you just know the states.
I would like this like the one state I know, I'd go there and go, to the right of Minnesota.
Yes. Come to office hours, young man. I could teach you the 50, and I'll teach you the never come 51st. Damn right about that. Not that anyone would ever think about it these days. Okay. So these are all excellent comments, and I think actually we can mine these some more, but I'm gonna supplement this with an experience from a totally different time scale, different context. This, your class members, is a depiction of testing on 3 projects: the Voyager project, Magellan project, Galileo project. Now, anyone know what those are? Yeah, Voyager 1, which was a spacecraft, right? Launched by NASA in the US, right? These are interplanetary, or in the case of Voyager, it's actually left the solar system now. And these are projects where they were developing software for them. And as a key component of it, you develop not only the hardware, but the software that accompanies it. And one feature of this situation for spacecraft is maintenance is hard, right? It's not easy to go repair a spacecraft that's out of the solar system, right? Or out circling Jupiter or what have you. So they have to be really, really careful about software quality. If something goes wrong and it stops receiving patches or whatever, you don't have really any options, right? And so they do very, very rigorous testing on the software. And the software, you might think it has to only do a few things, put out solar panels and orient the antenna properly or what have you, or change the orientation of the panels. But in fact, it's rather complex because it has to be really robust to things like cosmic rays from the surrounding environment. There can be high energy particles in space that our atmosphere shields us from here to a large degree, but in space they can hit electronics and cause bits to change, and it has to be robust to it. So there's some complexity there. And each of these projects, which were undertaken at very different times historically. They had to create software worthy of them. The software was of different size than Voyager's day. I was yet a young man, and then that would be stretching. I was young when Voyager was launched. But these other two are more recent. And what we see here on the x-axis, what we see on the graph is broadly a look at the cumulative defects or the density of those defects in the code base per 1,000 lines of code written for these projects. And I would venture, I don't know this for a fact, but I would venture that these were written in different programming languages because Voyager was, well, I'm not sure C was developed yet as a programming language. It was probably under development, or maybe it was before it at Bell Labs. But these later ones, I think there were certainly a lot more programming language integration. But you notice that the defects per 1,000 lines of code are in the same rough scale, right? At the top, 10 defects per 1,000 lines of code, right? 1 defect per 100 lines of code on average, right? 1% of the lines of code have a defect in them. Another way to say it, right? The x-axis is not hours of test, not days of test, it's weeks of test. Right? So if I were to say 109 weeks, what's that roughly? 2 years? Yeah, a little bit over 2 years, right? Right? Weeks would be 2 years. This is like 2 years of test. This is 2 more than 2, right? So they were testing these things for years, right? Voyager for a little bit less than 2 years, but the others for somewhat over. In the case of Galileo, up to almost 6 years, right? So this is showing defects found in terms of density, fraction of lines of code. Per 1,000 lines of code, how many defects there are for these projects over time. What do you see in this graph? So you can look at all 3 of them pretty easily. Do you see any of the features that you noted that were noted earlier? Anyone want to comment on? I think many of the things you had mentioned actually are reflected in this graph. Can you give me one of them? Yes.
Sure. I think at the beginning of time, we found lots of bugs, right? Defects.
Yeah.
And then after a period, you don't really find that much.
Yeah.
At the end, you might find a bit more right here.
Okay, good. So take a look at Galileo, right?
Yeah.
So it rises. And it rises more quickly at first. It kind of plateaus. But then there's this rise later. I'm hearing a lot about what Rob said, that you find them first more quickly. More quickly is a bit of a, put in context, right? It's like for the first 2, you're finding defects pretty quickly. And then it sort of plateaued off, but did it stop altogether? No. It didn't. And it continued on. And then there was this apparent burst at the end, right? So does anyone else see evidence of bursts here? Sort of punctuated, like if they find it and then it slows, but find again. Look at Magellan, right? It kind of goes up, flat. You may say, well, it's not that long ago. That's like a couple months at least, right? And then suddenly it's like, okay, they're onto something. And then it slows a little bit. Oh, they're onto something. And one of the things you find if you look at the literature, and I believe this was strongly to prove this from what I understand about the historic context in NASA, is they would find things in bursts. So they would find a certain class of defects that is indicated by just one they found. They said, oh, there's they thought about it, and it's like, there may be other things like this in the code base. We do this similar thing in this module and that module in this other area. And so they end up having the opportunity to look for this type of defect in many places. And they found, a whole bunch across the code base, and they mine that vein of ore, right? It's like you're mining a vein of gold, and then you kind of run dry. The vein dries up, and it's like, okay, let's keep on looking. And it's kind of slow going for a while, and then suddenly it speeds up. And you kind of see that in all of them, right? There's this kind of slow, and then up, slow and up, even in Voyager. But you see it as well, these kind of staircase patterns, don't you? And sometimes it goes on for quite a burst. They're on a streak, right? A winning streak to discover it, but then it's like. I also want to draw obvious, just make the obvious observation here. They were finding defects after years, right? Even Voyager, as the 2-year mark approached, it found some little bit of defects towards the end. And certainly for Magellan, they were still cooking, 1 to 2 years in. And Galileo, well, they were still finding things, good 3 years in. And it slowed, but they were finding some things as they were approaching like the 5-year mark in fiction. So finding defects takes time. It takes focused effort. It takes learning, right? And it benefits from thinking about what we found and where else could we find similar things? How can we learn from this defect about other aspects of our code base and about how to find those defects faster? So maybe it leads to a faster testing, a quicker innovation in testing. Oh, let's get a bunch of tests out that test for this sort of thing. Or let's get better debugging this sort of thing to remove these defects, right? Better at peer reviews that can find these defects. Think about that, right? You're doing peer reviews, you're doing inspections. I've been reading about them. And you want to think when you find a defect, like, could we have found this earlier, like in peer review? How could we find it in peer review? What could we change in how we do peer review that would be more likely to find something? These are things you want to learn from, and learn they did. And it's to their credit that learning leads to like bursts in finding defects. This isn't just chance. This is like capitalizing on the defects we've recently found to mine that ore, right? It's not just finding defects by stumbling around blind, right? Like an orange-haired menace, right? Okay. Making random utterances of menacing character. Nothing. For now. Okay, I want to talk about what underlies those. We've been referring to some features of it, but I want to talk about the structured process, the stages that defects go through before they get discovered. And once they get discovered, before they're fixed. And when they are fixed, the risks that they may be reported as fixed, they're not really fixed. They have the appearance of being fixed, but they're not yet. And then how those fixes might lead to, in the process, other defects, accidental, what's called defect feedback. So, you may not have ever thought to sort of formally structure their understanding of this, but I put here bug resolution pipeline, but it could be called stages in a bug cycle and defect cycle. Right? So if you think about software defects, they begin undiagnosed, right? Like when a defect is created, almost without exception, we'll talk about some exceptions that are used in like testing, defect seeding at some point, but virtually all defects start unintentional, right? They come about through one thing or another. Maybe it's a merge conflict that gets fixed the wrong way. Maybe it's, you know, trying to fix a defect that's trying to fix a problem that's complicated. You end up introducing another defect in the process. Or maybe you're writing code quickly and you make a mistake. Or maybe you misunderstand something about the stakeholder requirement and you wrote that code. But almost invariably it's inadvertent, right? You don't know that this defect has been created. And there's some big class of defects in the sky, so to speak, that are undiagnosed defects. They're there. We don't know about them. Again, occupational health and safety issues prevent me from standing atop this very desk. But if I could, I would, you know, convey to you in the strongest and most stentorian of terms that each of your projects has a stock, has a pool, has a set, a class of undiagnosed defects associated with it that are there and you don't know about. And your job is to discover them and to prevent similar things from getting in there in the future, right? This is all about discovering undiagnosed defects and discovering them first, right? Right? There are some defects in Voyager's code base that they were discovering. There are some defects in Galileo's code base that they were discovering for upwards of 5 years. Do you get my point? There are these undiagnosed defects they are discovering over time. And yes, you could say, well, there's bits of change to the code base being made to fix those defects. But a lot of this is fixing a pretty fixed code base, a pretty constant code base, being patched a little bit here and there, and just discovering a set of, mark my words, undiagnosed defects. Do you get my point? Okay, but that's just the birthing point of defects. Like how mosquitoes begin their life in a quack phase. It's a pupae in larval form. Come talk to me about the cells. We model said mosquito. And it's through a process of testing or a process of peer review. This says testing, but it's really can include peer review too. That some of these bugs get discovered and get reported as with issues created for them, right? Do you get what I'm saying? You understand what I'm saying? Those get discovered, they get identified, right? But these defect reports, these issues that got created, these bug reports, as we might call them informally, are not surefire things. Can you give me, for the initial reports of problems people report, what are sometimes called system trouble incidents or defect report? System trouble incidents is actually a better name suggested by Jerry Weinberg. But just be sure with your health science colleagues, like those who just took our photo, you don't use the going term for system trouble incidents, STIs, more glibly with our health science colleagues, because they'll misunderstand the nature of your concerns. Like you want to speak with them about the STIs for your project. And yeah, they may think you're talking about a certain type of viral infection, in the code base, right? So these defect reports, these system trouble incidents that are reported, what problems could there be? Why do I say those are not necessarily the real McCoy, the actual perfect knowledge of the problems? What, or even of the issues? What stops these from being an immediately reliable source of guidance on what defects there are? Why can't we just count those up and say we have 50 defects within our system that we've discovered? Yes, Rob.
We have multiple symptoms of one single.
Excellent. Yeah. Excellent. And this is very common. You know, glibly we might call them duplicate, but they're not strictly typically exactly the same thing. Sometimes they are reporting the same basic error message that comes up, but often it's different faces of the same thing, right? It's different symptoms of the same underlying problem, and it just manifests in slightly different ways.
You miss a opposing bracket or frenzy, you've got 50 things that are not interpreted properly.
That's right, but they're all from that one thing, and this is pretty common. So you get things might be called duplicates here, and I'll use that word bearing in mind that it's kind of it's not like they're exact clones of each other. They're different symptoms often of the same cause. What's another issue you might have there? That means you can't trust it as like a perfect report on the defects found, a fully trustworthy report. Well, some of them could be outdated. They might have been for ID2 or now going forward as you venture into ID4. They could be for ID3 and they're now outdated. Maybe, right? Maybe the code base has been updated since then. Maybe there's been a patch put in place in the past that's now fully fleshed out in the system, and that you're now reporting something that is about to be released in the version about to be released has been fixed, right? So some of these are kind of outdated. What else could go wrong there? Yes, Alex.
Sometimes people report intended behavior as a bug.
You got it. Sometimes there's misreading of what the behavior should be for this case. And this is actually by design, it behaves this way, but they didn't realize it. It was the result of a requirements change that came up in a last discussion they weren't part of with a stakeholder, right? Maybe they didn't know you weren't implementing this feature yet. And that's for ID5 or something like that. And they report this as a problem, but no, that was actually part of the plan for ID4. We're not doing that, right? Could that happen? Darn right it could happen. Yeah. So outdated things, duplicates in a loose sense, but recognizing at different symptoms of the same problem, incorrect understanding of the defects, right? Now, this next set is called active bugs. In the process, this is really important. When we think about change over time and the defects you find, when you look at those reports from NASA, and when you think about those reports for your projects, before things can be turned into reliable reports that are not do not include that are scanned out, outdated ones, that are not based on misunderstandings or requirements, that have been validated for being confident, genuine problem, right? Genuine issues to be resolved, defects. That process is called sanitization, okay? Bug report sanitization, defect sanitization. And it involves taking these and weeding out those that are duplicates or consolidating into one. Removing those that are outdated. That been maybe languishing here, and a new version has come out that fixed it or renders it moot because now the implementation has changed, and that's a past issue. And so these defect reports get sanitized, and then they become active bugs. These are, and that's the term of art for it. These are like active defects. These are actionable defects in the sense that they are representing reliable understanding there are problems to be fixed indeed, Mhm. They're not duplicates. They're not outdated. They're not based on misunderstanding. They're reliable guidance on things to be fixed. Now, these active bugs are good candidates to be fixed. What might lead you to decide whether or not you fix them? Well, let me ask this. I mean, are you going to fix all of them? Why not? Why Rob shakes his hand and he's correct. You're not going to fix all of those, even those active ones. Why not, Rob?
The cost, so in terms of like time, manpower, it's like about like fire costs. Probably got like above reports, so above the 10-year old and everything fixed.
That's right.
At the cost of you on.
Cost, time, because they will soon be moved, right? Like development will soon render them moved. Plan development. Here's another thing: risk. Why do I say risk? How could risk lead you to not? What sort of risk might lead you to not try fixing a defect? Anyone? Like why might it be a consideration against fixing? Yes, Connor.
I feel like if your system relies on that functionality and it's like a single person needs it fixed, you might break it again.
You might break a lot of other things. And there might not be time to discover those things you've broken before you have to go live, go into production, deliver the system, right? You have the devil you know against the devil you don't know, right? And you might not have time to even know these new things are there, and you don't know how severe they are. So maybe the one you know is of moderate severity, there's a workaround, you know how to deal with it, you guide the stakeholder, you know, about how to make it less of an issue, so it's not a problem. You can document it, you can plan around it. But the ones that you introduce by trying to fix it, or the ones you could introduce, might be who knows what level of severity. Might break the system, and you don't have time to test it. You don't have time to go do peer review on all these things. You could end up leaving the user with a really broken system without realizing, because you don't have time to do the requisite quality control. This is a key point, right? Imagine you're 6 hours before going live, you have this defect, you know about it, you can either document it really well and give a workaround to the stakeholder, or you can try fixing it. It's kind of a Hail Mary pass sort of thing. Like you're counting on this working, but you don't have time, and that's really risky to try to fix it. Why, right? So a lot of these active bugs, you don't actually immediately fix. They are there, you know they're there. They're not defects. They're not duplicates. They're not outdated. But only the ones that undergo what's called a triage process, typically by project manager or combination of the project manager and dev or test lead, will lead you to triage those and say, which ones are we going to fix? And these go what I call important bugs, but this is actually a poor name for them, okay? These are the next stage, the ones that have undergone triage, so the ones we're choosing to fix. We're choosing to fix. We're going to give them to someone to fix on our team. And they get assigned after a bit of a delay to some developer, right? Maybe she works on them, works to fix it, and marks it resolved. Right? Some systems we call it fixed. Any of these developers might choose to work on it, and they deposit it there. And maybe there's developer A, and he goes to fix it and marks it fixed, but we don't view that necessarily as a guarantee it's fixed. So there's two issues here. First of all, the developer may not have actually fixed it. Why do I say that? how could it be the developer thinks it's fixed, but it's not? Could you give me a couple specific reasons, scenarios in which a developer may think it's fixed, but it ain't? Yes, Randall. It introduces a new bug as a possibility, and we'll talk about that in a minute. But I want to focus on the case of, is the thing that this developer is trying to fix, why is it that they may think it's that particular thing is fixed when it really ain't? Yes, Connor.
So they have like, it passes the tests that are there, but there's no tests that others for, so it passes like, you know what I mean?
Okay, yeah, so it may pass those that are there, but it may be that there's still some problem with it. They haven't really fixed. And by the way, this is one of the reasons why when they go to verify it's fixed, like that developer, she may add a couple unit tests with it that really verify it's fixed, right? And document it. But what's another reason that it may not actually, so that's true, the tests are inadequate to purpose, that they don't recognize some problem. It passes the suite, but it doesn't fix the real problem. What's another reason? Anyone? Kenner, yeah. Yeah, they didn't find the root cause, and so they think it's fixed, but actually it didn't deal with the real issue. They thought, I think it was just due to this, but actually it was more complex. It was a more complex story, and they didn't dig into it and fix the underlying issue. And so it was a band-aid thing which didn't really resolve the issue. It was a super big. What's another reason you think it's fixed? It's not. It's actually quite a big issue. Something else. Because they don't want to believe it's a problem. And they say, this is how it's supposed to behave, and they're bull-headed about it, and they want to show that it's right, but maybe they don't read the bug report closely enough. Maybe they don't really understand what is being reported, and they think it's a superficial thing, and that it's actually not a problem with the code. It was a problem with the tester. The tester doesn't understand how to test it. Doesn't understand how good my code is, or whatever, right? And I mean, I'm speaking in a jocular way, but the truth is that sometimes developers have to be really careful with ego, because when they read the bug report, it can sometimes bring up difficult emotions. You put your heart into this code, and now someone's saying there's a problem with it, and sometimes you don't want to believe that. It's inconvenient. It doesn't make you feel great. And you got to put those things aside and ask objectively, is this a problem? And sometimes people are a bit too glib, especially if they're under pressure. They're working long hours. They're juggling a bunch of problems. They're a bit too quick dismissing it and saying, look, I fixed this problem before. This is not really an issue. It must have been a problem with the reporter. I can't. You ever seen someone say, like, works fine for me? I don't see a problem. Doesn't happen to me. I don't know what you're talking about. You say it had a problem. Works on my phone. You heard that? Like the bane of our existence sometimes. Yeah, and it's a real problem, because it is convenient for them to put it aside, but often there's a real issue. This gets into what Tanner was saying. There's a hidden underlying issue. Maybe it works on their phone. It's not denying that. Maybe it works on their phone. But that doesn't mean it works on other people's phone necessarily. And sometimes you have to be really like, show it to them, right? Like, it's like, this is not my imagination. Yeah, developers are people, testers are people. And sometimes there's a bit of a, I see some knowing smiles in the audience. And so these things are part of the human theater. And there are times where it's actually not fixed, and it actually goes back and it's discovered as not fixed. But sometimes it is resolved. Maybe she fully resolved it, and it gets closed. And it gets marked as not just fixed, not just resolved, which I'm using as synonyms, it gets closed. It's a closed issue. Maybe it's the project manager, the people, or the test team, or the end user who experienced it, or the stakeholder who experienced it, they mark it as closed. I'm satisfied. It's gone now. It happened on my phone. It doesn't happen anymore. I'm going to mark this as closed. Okay. But Randall said it earlier. And as normal, Randall's onto something. This can cause defects, new defects, right? So regardless of whether you fix this particular one, there can be defects created by fixing it. The statistics on this are not very good. The statistics suggests, I think it's somewhere around 20 to 30% of defect fixes involve fewer than 10 lines of code. I think I have the statistics here, but it's a large fraction. I think it's like 20 to 30%. If they require 10 or fewer lines of code of changes, they introduce new bugs. 20 to 30% of the time. If it involves like 100 lines of code, the chance of introducing new bugs is way up there. It's like above 50%. Fixes breed new defects. Attempted fixes. Even if they fix the problem, it's like you squeeze a balloon here, it pops out there. Ever been in that situation? You fix it here, now this doesn't work. Fix it there, that doesn't work. Huh? You know these things? What's that? Whack-a-mole. Whack-a-mole. Exactly. So new defects get created. And one of the key things is there's a long delay before these get perhaps reported as defects, before they get sanitized as reliable defects. And so if you've got to ship soon, you may be fixing a bug, but you've introduced new defects that are yet undiagnosed. And the cycle continues, and you might not discover these before it's in the user's hands and it stops working. Certain features stop working for them. So this is a bug's life. I've written this out in some sort of longhand, but you see it in evidence here. Things take time to discover. Things get discovered in bursts, and it takes a while before things convert. So, the point I want to hear with my key principle in software development and in life. When you make mistakes, maybe it's mistakes that manifest in the form of a defect or in other areas of life. It's helpful to ask yourself, how can you do better next time? And specifically, how can we prevent this in the future, a defect like this? Or if it happens, we slip up, how can we discover it more quickly? Right? That's really what you see here is, discovering things quickly, right? You learn from these mistakes and you're on a roll. And you discover a whole sequence of defects quickly. You learning from your mistakes. You make a mistake, it's easy to view it as a failure and inability to move forward and moving backward. But truth is, it's a huge step forward if you can learn from it how to avoid similar mistakes in the future, or how to discover them if they are made. You discover them more quickly. And much of what software development is about this process, right? When you find a defect, don't just fix the defect in your code base, fix the defect in your process, in your development process, in how you spread knowledge in your team, right? Because it may be that the person developing this, maybe the defect crept in because they didn't understand how Jest interacts with, React, and they ended up thinking the defect was fixed when it really wasn't, or the defect came in because they didn't understand how Firebase worked with the back end of your system or what have you. It could be that you hooked up your game in terms of inspections and peer review, in terms of how pair programming is done, in terms of the tests that are involved. This is how NASA found things in these big bursts. It's capitalizing what we found to figure out how can we mine that vein of gold to find more, and how can we prevent similar defects, in our code base from coming in. And it's one of the reasons this plateaus, right, after a while, or with Voyager plateaus. They get better and better at what they're doing. So often we can generalize from a discovered defect to improve not only prevent, to find out these defects in the code base and to identify them and fix them, but we can also prevent similar defects in the future. But there's another form of learning that goes on. And this is a process I would like you to consider using in your teams in the coming weeks. And it's called directed triage. It's different from this triage we talked about here, which is really about figuring out which bugs we're going to fix. Directed triage is a learning process of learning. Okay. It involves systematically wading through the defects at these stages, particularly bug reports that are not yet sanitized, but even those that are active and waiting there might be a big queue of them, 100 of these active defects. And basically directed triage systematically goes through those and said, where are we at with our software? Like, what's the quality level? Are we ready to deliver? Are we ready to go into production? Are we really ready to ship our system? And it's really designed to resolve uncertainty about where we're at. Because if you've got a bunch of bug reports that are not yet sanitized, might be a lot of defects. Maybe there's symptoms of the same defect. Maybe for every 10 defect reports that are in there that have not yet been sanitized, really there's only one real problem, right? Maybe a lot of them are outdated. And even the active bugs, maybe many of them are lower priority, or they're not really things that should get in the way of the delivery. Maybe some of them are higher risk to fix. And so directed triage basically goes through defect reports and says where we're at. Like, how bad is the defect situation? By looking at those defects and sanitizing them, that's a lot of it. And with the active bugs, figuring out how serious they are, how hard is it going to be, how risky is it going to be to fix? And figuring out basically what's the quality situation. And it's especially geared towards, can we go into production? Can we go live? Can we ship our system? Can we push it out to users for their phone? Do we go post this on Google Play Store and the Apple Store, or should we hold off from that? Right? So direct triage is a learning process. It's not just triage. What are we going to fix? No. Studying where we're at, resolving uncertainty. As long as they're in this stuff here, this pool here, bug reports, we really don't know that much about them. There might be 200 here, but they're really, really only 15 missing people. And so we need to go through those, and we need to reflect on our active bugs, their priority level, how urgent it is to fix them. And we get a sense of where we're at, and are we ready to go into production? What do we have to fix? What do we must have to fix before we can go into production? What things are low enough risk and high enough return in terms of, the functionality will guarantee by fixing them that it's in fact worth fixing. So this is a process of deliberate learning. Do you understand that point about directed triage? Okay. Now, I want to talk a little bit about the sort of dynamics of this process. So this is what's called a stock and flow diagram. Okay. It's a type of modeling diagram, and we use it with quantitative models as well as more qualitative models. And I want to reflect on a situation here, and it specifically has to do with defects being found. That's here. We're finding defects. Maybe it's in testing, maybe it's in peer review, but also bugs being fixed down here. Now, here we have over time, this is days in a slow-moving project. It could be, well, maybe it's weeks, given the scale here. This is the number of defects found per, say, week. Right? Week 3, we have 200 defects. Okay. Right up there. These are the number of defects fixed per week in the magenta. So on week, let's take this one. On week 3, we had about 140 defects fixed, right? You get that sort of situation. When are there, over time here, when are there the largest number of identified but not yet fixed bugs? Still defects. When is that the high? Anyone? Who that? Okay, bugs found. This is one idea. Anyone? So that's an idea for when the number of defects not yet found, or that have been found but are not yet fixed is high. Does someone else have a different idea? Rob?
Would it be when he identified and fixed one? I know this.
Because if you think about it, for all this time, the number of bugs every week successively, right? In this first part, there's more defects found than there are defects fixed. So give credit to Udav. He noted the defects found here, 225 or so in week 2 is the highest. But let's consider how many defects there were that week. After that week, there's a lot of defects that have been found but not yet fixed. But whatever that number was, by the next week, there's even more because we fixed fewer than we found that next week. So there's more coming in than have left, right? It's like water is coming into the bathtub faster than it's leaving, right? It's coming in, like the gap between how quickly it's coming in and leaving is the biggest here. But so it's rising the quickest in this one, where it would have said, but it's still rising here because water is coming in 2 liters a second compared to leaving at half a liter a second or whatever, right? Compared to 1 liter a second. It's coming in faster than it's leaving, so the bathtub is still rising. Coming in faster than it's leaving. If you want a more graphic example, you could think about a stuck toilet, right? If the water's coming in faster than it's leaving, the water's going to be rising. Water's going to be rising, and you better get that plunger ready, right? So it actually keeps on rising until these 2 crop. What happens after that? You're now, what's the feature of this situation after that where they cross?
After equilibrium, then the direction shifts.
Yeah, you're fixing more defects per week than you're finding. So the number of bugs that have been found but not yet fixed goes down. It's going down. What happens these 2 weeks? Maybe it's week 9 and 10. What happens between these 2? There's no change, right? Number of defects being found is the same as number of defects being found. Being found is the same as number being fixed, right? So it's staying the same. It's like water's coming into the sink as fast as it's draining. Stays the same. Do you get a sense of this? Right? Okay. So commonly in a project, the number of defects that are there that have been found and not yet fixed actually is rising at first. You're finding things fast and you can fix them. At some point, hopefully, things are starting to stabilize and you're keeping up with it, and the number of defects may still be going up cumulatively, but you're keeping up with the number of defects that are active and or found in, to be evaluated to be active is constant. And at some point it will start to go down. Now, software projects have made like larger software projects have tried these sort of things very seriously. So tracking system trouble incidents, active system trouble incidents. These are ones that have undergone what process? Active ones have undergone, begins with S. Sanitization. And commonly in that process, at the latest, commonly we do it before then, but at the least we do it then, we label things by severity and priority. What is severity and what is priority for a defect? Can anyone say? Okay. Yeah. So Connor?
Severity would be like crashes they're not, priority would be like how.
Yeah. So severity is how bad it is if it happens. This should remind you a little bit of risk management. This idea, like you evaluate how bad if it happens, and then priority takes that into account. A crashing bug is pretty bad, but if there's a very low probability it occurs, or it occurs only on systems you almost never see anymore, right? Under rare occasions, right? You have to be disconnected from the web and have very little memory left in your phone, because other apps are using it. Only then will you see it. It might be low priority. The priority is urgency and fixing is one way we sometimes view it. Another thing is we consider probability of its occurrence and the severity, and we consider both those. And so something may be high priority, but high severity, but low priority because it's so rare. Can you give me something that's low severity, but it's going to be very high priority if you're a stakeholder? Low severity, it's not going to crash it. It's not going to corrupt data in your system. It's not going to lead to wrong information being delivered. Directing people to a vaccination clinic for the wrong vaccine or something that doesn't have their vaccine within. Yeah.
Yeah, like it's low severity, but it affects like all systems, let's say. Like it affects a broad swath of users.
Okay. So it affects, so be seen by a broad swath of users. Yes, Marcia.
Yeah, for example, say if for stakeholder like their brand is UI design.
Yes.
It's a very high priority about low severity.
That's right. So maybe they really want a certain look to it. They really care about this look, that it be consistent with Saskatoon Health, or the Saskatchewan Health Authority look. Or maybe it's a misspelling, maybe it misspells Saskatchewan. Can you imagine that? Closest. Yeah. Closet. Yeah. So it misspells something obvious. And it's embarrassing, right? The splash screen comes up and says something, says something crazy, right? Microsoft or something like that. Microsoft Word, like that's not severe, but it's pretty high priority to Microsoft to fix, right? So we often distinguish those. Percent of tests that have actually been evaluated and sometimes that's broken down into test steps, and then percent of tests that have run successfully, meaning they actually passed. Defect data at closure is sometimes used. That has to do with like how long it is between when a bug is reported and when it is confirmed, fixed, when it's closed. How long is that? If this is a month, it's going to take a while to converge. There's a long time here till it gets assigned to developers, till we find, yeah, it's a valid bug, it's sanitized. If there's a month here, we're going with a very slow cycle time. If it's a week here, you're not doing too badly. If it's a day, hey, you're keeping up with that very well, and you're right on top of it. Fault feedback ratio. This is a key one. I mean, one that of which Randall spoke, and prescient. Defects, attempted defect fixes sometimes breed new defects. And organizations will sometimes track this. You know, like how many fixed defects they end up discovering a defect coming from that fix. You may not think that's that significant, but it's really significant because you get the risk that you fix something and then it's the devil you don't know in the code base, and you won't know it for a while, and it inhibits being confident enough to ship, right? If you're getting these at high number, and it also leads to time till it converges that can be quite high. So often, and I would say this for your project, often you really want to treat bug fixes that occur late in a deliverable as you're approaching the deliverable. As you're approaching going into production or delivering it to your stakeholder, or even the professor, you will want to fix very carefully. Like you'll have 3 people who know this area of the code base clustered around and, you know, sharing their screen via Zoom and talking about how they're going to fix it, seeing if others have any concerns, and actually doing pair programming to fix that defect. Make sure it's done right to prevent a circulation of defects where suddenly we have a new one. The statistics on these are grim, and yeah, I don't have time to show it here, but that was a little bit on the dynamics of defects. The testing, the QA process, and stages in bug slides. Okay. Next time, in response to student needs, I'm going to be talking about assertion and their proper use. I'm going to be talking about error handling and its use relative to assertion. And I'm going to be talking about some performance issues that come up with ways of handling errors like exception. Okay. And other ways of handling them that are more monadic. Anyway, we'll talk about this next time. Thanks very much. I'm meeting with team 3 on Monday. There's one team we haven't scheduled yet, right? It's team 1, I think. Yeah. And I really want to try to find a time to meet. Okay.